When a major highway bridge drops into a river, you assume it was just too old. Or you assume the rush hour traffic and the heavy construction equipment on the deck finally broke it. By the end of this file, the investigation will show exactly which calculation error guaranteed the collapse before a single truck arrived that day.
August 1st, 2007. The I-35W Bridge in Minneapolis. An 8-lane steel arch spanning the Mississippi. It carried 140,000 vehicles a day. It was 40 years old. That afternoon, a construction crew staged 578,000 pounds of raw material directly on the deck. At 6:05 p.m., the center span gave way. The public narrative immediately blamed the weight. But the investigators didn't look at the traffic. They looked at the joints. When the National Transportation Safety Board opened the file, they found something buried in the original 1960s blueprints. This is a gusset plate. Its only job is to hold the massive steel beams of the truss together. The board's finding was precise. The U-10 gusset plates were inadequately designed. To understand why a steel bridge falls, you have to understand exactly what a gusset plate is supposed to do. At node U1, 4 different beams meet. The forces from the traffic above and the bridge's own weight all converge here. The only thing transferring that immense, crushing energy between the beams is the flat steel plates bolted across them. They are the central nervous system of the truss. If they are strong enough, the bridge stands. But the plates at U10 were not strong enough. And the error wasn't made by the traffic. It was made by a pencil in 1961. When the bridge was designed, engineers calculated exactly how thick every plate needed to be to handle the maximum expected load. The process was manual. Thousands of calculations for hundreds of joints. And somewhere in that math, node U10 was calculated wrong. Based on the load it was carrying, the plates at U10 required a thickness of exactly 1 inch. They were fabricated, installed, and approved at 0.5 inches. Half an inch. 50% of the required strength was missing on the day the ribbon was cut. Which raises an obvious question. If the joint was built at half strength, why didn't it fall immediately? Because bridges are designed with massive margins of safety. A plate built for 10,000 pounds usually only sees 4. But because U10 was designed half as thick as it should have been, that entire safety buffer vanished. For 40 years, the plate survived right on the edge of its yield point, silently holding back the weight of the highway. And then, slowly, the institution began adding weight. In structural engineering, this is called dead load, the permanent weight of the bridge itself. In 1977, the bridge was modified. The deck was thickened by 2 inches, more concrete, more dead load pressing down on the undersized plates. In 1998, they modified it again, replacing the steel guardrails with heavy concrete barriers. More weight. Still no check of the original math. By the time those modifications were done, the bridge's dead load had increased by 20%. Node U10 was now carrying forces it was literally never designed to hold, and it began to bend. In 2003, a contractor took a photograph of the U10 connection. The bowing was visibly captured on camera. But because inspectors are trained to look for rust and cracks, not original calculation errors, the distortion was not fully recognized. When you inspect a bridge, you assume the people who built it 40 years ago got the math right. But the bridge was aging, and the state knew it had structural issues entirely separate from the unknown gusset plates. Which brings us to the documented trail of what the institution actually knew. The federal government has a specific classification for bridges with advanced deterioration or poor condition. It's called structurally deficient. It doesn't mean it's going to fall tomorrow. It means it requires immediate attention. The I-35W Bridge was officially classified as structurally deficient. Inspectors repeatedly recommended that the bridge be reinforced or entirely replaced. But replacing a major artery costs millions, and state budgets are finite. The massive structural retrofits were repeatedly deferred. Minor repairs were prioritized to keep it open. And so, an undersized gusset plate that was silently bowing under decades of added concrete was left holding up a bridge the government already knew was deficient. When you drive over a bridge, you assume the timeline of its safety is linear. But safety timelines don't run on physics. They run on paperwork, and paperwork waits for budgets. And a structural deficiency doesn't check the calendar before it fails. Physics doesn't wait. The federal government classified the bridge as structurally deficient in 1990. The retrofit was deferred on cost grounds. The bridge collapsed in 2007. Which brings us to the afternoon of August 1st. The state was replacing the concrete driving surface. To do it, the contractor staged their raw materials directly on the bridge. 578,000 pounds of sand, gravel, and heavy machinery. They parked it in the closed lanes, right over the center span, directly above the 1960s calculation error, directly above the undersized bowing plates of node U10. The yield limit wasn't just reached, it was obliterated. At 6:05 p.m., rush hour traffic was barely moving. Beneath them, the gusset plates at U10 finally tore in half. The main truss was suddenly disconnected. The load had nowhere to go. A 1,000 feet of steel deck, 50 vehicles, and the entire construction crew went into the river. When a bridge fails this way, the investigation isn't just about finding the broken piece.
It's about proving exactly how an error made in a drafting room in 1961 survived undetected for 40 years. The U-10 plate wasn't rusted away. It wasn't fatigued by age. It was simply built too thin for the weight it was eventually asked to carry. 13 people died. 145 were injured.
When the NTSB pulled the U-10 plates from the wreckage, they found them fractured, exactly where the math said they would. The final report was issued in November 2008.
It formally cited the design error, compounded by the decades of added weight and the concentrated construction load. But a forensic investigation doesn't just explain why one bridge fell. It rewrites the rules for all of them. Before 2007, bridge inspectors weren't required to calculate the structural capacity of existing gusset plates. They assumed the original math was right. After I-35W, that changed. Every non-load path redundant steel truss bridge in America had to be re-evaluated. And when they finally ran the math, they found other bridges with the exact same 1960s calculation errors, a pattern this file is going to keep tracking. Which leaves you with a different way to look at infrastructure. The safety of a bridge isn't just in the steel and the concrete. It is in the unbroken chain of assumptions. The assumption that the person who designed it got the math right, that the inspector knew what to look for, and that when a structural deficiency is found, the timeline to fix it will be dictated by reality, not by a budget committee.
The I-35W collapse exposed exactly one calculation error from 1961. But there were millions of calculations made in that era, for thousands of structures still standing today.
The math is quietly holding until you add just enough weight to prove that it isn't. The node U10 calculation error. Status. Documented. Known. Video number 007 filed.